Welcome to the next lecture in the BIM Basic series. Last time we talked about information and management processes in contracts that use the BIM methodology, and today we will talk about several BIM related issues. We will start with visual programming, which will have more to do with exercises using Dynamo. Then will be an introduction to generative design and artificial intelligence in construction. Next, we will discuss lean construction and integrated project delivery, building life cycles, as well as asset and facility management, structural health monitoring, and, and finally, digital twins.
We start today with visual programming, which is very useful in BIM modeling. Visual programming languages are programming languages that allow users to create programs by manipulating program elements graphically rather than building text structures. They enable programming to use certain visual expressions and spatial arrangements of text and graphic symbols that are used as elements of syntax and secondary notation. Programming work usually consisting of joining together frames or other graphic objects that are treated as entities. Connections between them, usually in arrows, lines, or curves, represent relationships between frames. The use of visual programming languages allows for easier modeling of complex processes and geometric relationships. Their popularity is since people without specialized programming knowledge learn to create advanced software faster using for this purpose graphic symbols instead of difficult to remember text rules and keywords. This is certainly helped by the increasing computing capabilities of computers and more convenient graphical interfaces. Architecture and engineering are particular areas of use for these languages. Highly complex spatial issues are easier to model using graphical programming, creating predefined procedures for parametric generation of more complex or repetitive structures. Initially, the development of these tools concerned only narrow specializations, mainly in electronics like Simulink or LabVIEW. Created by National Instruments, LabVIEW language is currently one of the most powerful graphic programming languages used in digital signal processing. The Grasshopper 3D language is trendy in the architectural industry, which works mainly with the Rhinoceros 3D environment and many other CAD and BIM tools. It is used, among others, to the so-called generative art, which is currently one of the new styles used in architectural design. Autodesk is developing similar products in its Dynamo and Bentley systems with the generative components tool. Usually, these programs' environment is open and the codes cannot be secured or compiled. Programming work consists of managing connections between program nodes, it looks like boxes, to create a sequence of events leading to a specific algorithm's execution. Nodes consist of inbound and outbound ports and have specific data and methods. Connections between nodes are created using the so-called wires that control the flow of the data in the program. The dynamic graphic language is based on Scheme text language, which is a dialect of the Lisp functional language, previously known mainly from AutoCAD. In this language, I wrote the first version of my best cut many years ago, which you may have already used. Especially nodes coded in Python can complement Dynamo. Here's an example of using visual programming to create a parameterized model of the structure reproducing a helix pedestrian bridge concept in Singapore. The object consists of two mutually interpenetrating steel spirals of different diameters that form the lattice. Inside, there is a platform, a deck, adapted to pedestrian traffic, from which cantilevered observation decks have been laid out at regular intervals. Construction begins with the generation of B-spline curve described by 3 points suspended in three-dimensional space. In the second stage, points are placed on the bridge's created axis, which divides into regular intervals. A properly processed matrix of points reflects the location and curves of individual bar elements of the bridge. On their basis, matrices of curves, surfaces, and other quantities are then created, inheriting properties from the previous code steps. The bracing system of the modeled bridge is already constant and cannot be directly parameterized. Therefore, it had to be re-established. Similar limitations apply to the bridge support, where only the possibility of changing the height above the established reference plane is provided. Such a parameterized model may constitute the starting material for further analysis. They can be carried out further in the Dynamo environment or transferred to the other programs like Robot or Revit. Changing the geometric parameters of the bridge allows for smooth updating of the structure in almost real time. We now move smoothly from visual programming to parametric, computational, and generative design. The presented example of parametric modeling of the helix bridge geometry is only an introduction to more advanced methods of structure design, which use parameterization of or static formulas coded in programming languages and introduce a high level of automation to design process and even elements of artificial intelligence and cybernetics. Especially when the project's goal is not just the geometry itself, even if the most complex one, but obtaining a certain optimal solution from the point of view of various criteria, not necessarily geometric. These can be, for example, construction costs and time, durability and functionality, energy requirements, or a carbon footprint. In such cases, it is necessary to analyze a huge number of variants, options, which are influenced by many parameters, and then select the best solution from among them, which, to a certain extent, will meet the requirements assumed at the beginning. With the advent of CAD techniques in design, there were also the first attempts to algorithmize and automate the design process. One of them was the CRAFT system developed in 1963. It used heuristic algorithms to optimize spatial locations or patterns of objects in the production plans. Simultaneously, it was limited to designing topological relationships between different parts of an industrial building without dealing with geometric descriptions of or offering a user interface for it. With the emergence of the BIM methodology and the first tools for modeling information about a building, interest in architecture techniques has increased. Although the community of architects was initially critical of attempts to algorithmize architectural design, architects became the main recipients of new trends over time. They even actively participated in the creation of the new concepts in this area. These include phrases describing these new approaches to design, such as parametric designing, computational designing, and generative designing. Unfortunately, it has not been sorted out even in English, and Polish architects often use these phrases interchangeably. There have also been no attempts to define these concepts concerning the modeling of building objects. Therefore, please forgive me for trying to deal with the problem of putting them in order. Um, Consider this as an introduction to the discussion of the use of artificial intelligence elements in structural design. In the traditional approach to design, an engineer or design team implements their ideas and concepts by creating a new model of the structure in various representations. Let it be bridge, various representations and forms. For example, in the form of drawings, calculations, descriptions, etc. The process is subject to many limitations that prevent too many variants from being produced and analyzed. These limitations are often time regimes resulting from the project schedule and technical difficulties that result, for example, from the lack of full access to information at a given stage of the idea's development. The simplest improvement that can be applied, even using CAD techniques and certain BIM methodology, it is algorithmic approach. The design objects are described using a set of parameters in the form of variables and constant values. By defining relationships between parameters, it is possible to create more complex structures than in traditional design. I call it a parametric design, and I showed selected four parameters of the arch girder we can see here. However, we are still dealing with a passive approach in which the designer, using his own experience and intuition, selects a combination of parameters that suits him. Both the number of all generated solutions and the variance that can be analyzed is limited. The next step towards automating the design process is additional support for parametric design by dedicated software. It is possible to describe the relationship between defined parameters and create scripts coded in a text or graphic manner. Scripts can be used to create both complex structures and greater number of possible solutions than before. But it still happens passively because it is the designer who has to decide on parameter values or the code's operation. This approach is called computational design, or other ways, computing designing. On the other hand, an active approach is a generative design and accompanying called optioneering. That's an optioneering approach. It is a fully iterative design process that uses both parametric and computational design elements, but with optimization algorithms. The designer determines the ranges, limits, and preferred values of selected parameters. The algorithm, examining many possible parameterized solutions, looks for those that best meet the given criteria. Genetic algorithms are often used to mimic nature's evolutionary approach to design through the genetic variation and selection. Here we see an example of an arc girder analyzing using a generative and variant approach. They require a parameter space to be defined and at least one mathematically defined, usually multi-parameter object function, also called a fitness function. Assuming certain parameter values, a solution image is generated. The example uses four parameters: arrow of the arc girder in meters, number of hangers, angle of inclination of the first hanger, enumerated type parameter identifying the arrangement of hangers. 0 means vertical, 1 radial, W type is 2, and finally mesh as 3. Dynamic change of the value of each of these parameters results in a change of the optimal solution. The solution is the variant that corresponds to the lowest or the highest value of the matching function. In this example, two opposing functions are specified: the cost of construction and maintaining the facility. Uh, we intuitively know that the persistent desire to reduce construction costs, for example, using cheaper materials or endlessly reducing the amount of concrete or reinforcement, must start to reduce the structure's durability and consequently increase maintenance costs. In this case, the optimization problem solution is not a single variant, but a set of solutions called non-dominated. They are often depicted in graphs describing the vertical and horizontal axes with the two different fit functions values. They are then plotting points on the graph representing a specific solution and its corresponding evaluation function values. The points at the edge of the solution cloud form a non-dominated solution front, also known as the Pareto front. The remaining points of the graph lying outside the front are defined as dominated, and they form a space of suboptimal variance. The color and size of the circle may determine the other components of the assessment. The generative design will be used more and more over time, mainly due to new, more friendly programming environments and simplified methods of creating scripts in them. They are now available and easy to use, even for designers with little programming experience to put their ideas into practice. When they can be associated with the construction industry's automation and progressive robotization, such as 3D printing, a great example showing such synergy is the product created by MX 3D robot, which were created using the generative approach. They also include the first steel bridge printed in Amsterdam. From here, it is very close to artificial intelligence and machine learning. Research on artificial intelligence has been in development since 1956, when artificial intelligence was first used. It was proposed by the American computer scientist John McCarthy, who is the creator of, among others, the Lisp language. This language may be familiar to older AutoCAD users. Artificial intelligence was then defined as a system's ability to correctly interpret external data, search for connections between them, and use this knowledge to carry out specific tasks while adapting to the changing situation around it. Today, artificial intelligence is a comprehensive discipline that encompasses computer science, cybernetics, information theory, psychology, linguistics, and neurophysiology. It uses, among others, fuzzy logic, evolutionary computing, machine learning, and robotics. The main goal of research on artificial intelligence is to construct machines and computers algorithms that would implement selected functions of the human mind. It is about solving difficult tasks to algorithmize and require the analysis of enormous data sets numerically. Considering the needs of civil engineering, such a task certainly include optimization issues. Rational reasoning knowledge management, expert and diagnostic systems, and supporting decision making in conditions of both limited and huge amounts of data. Observing the research conducted worldwide on the use of artificial intelligence in construction, one can notice a growing interest in these algorithms and a large and unpredictable potential. Artificial neural networks are closely related to artificial intelligence. It is an information processing system that is structured and functions somewhat like fragments of the actual nervous system. The most important feature of a neural networks is its ability to learn from examples and automatically generalize the acquired knowledge. For example, generalization. One of the fastest developing methods of the practical application of achievements in artificial intelligence is the so-called machine learning. There is no single consistent definition of this approach in this case. Still, in the original meaning, it was the ability of computers to learn new or improve their skills, but without re-interfering with the algorithm. This technique allows programmers to replace a series of conditional statements using if statement with generalization rules. Machine learning remembers certain patterns and behaviors which are then compared with newly accurate data. Based on previous experience, the machine or algorithm looks for a solution guided by the training stages rules. Most of the machine learning algorithms were developed in the 1970s, but it was impossible to use them in practice due to insufficient computing power, especially when it comes to training or other ways learning. We need to provide a huge amount of data like images, sounds, signals, behavior descriptions that must be analyzed and used for prediction. There are three types of learning: supervised, unsupervised, or reinforcement. In supervised learning, input and output data are simultaneously entered into the system. On this basis, uh, it creates appropriate rules that should allow to make conclusions on its own in the future. Thus, it should be able to assign the correct output to an object that was not previously in the input data set. In unsupervised learning, the expected output is not provided. The algorithm has to find the right rule that describes the input and propose a generalization of the problem. In contrast, reinforcement learning assumes that the machine operates in an unknown environment. There is neither known input nor output in it. It only receives the information in the form of a gain signal. It can be positive, then it will be a reward for the right decision, or negative, then it will be a punishment for making a mistake. Here we have some other variations of machine learning in use graphically shown, but we won't discuss them anymore. An important area of machine learning application is the analysis of the large data sets called big data. Such collections can be, for example, data stored in building or bridge management systems in which the inventory of resources may contain hundreds of thousands of bridge structures with all knowledge about them, with digital models and a record of events from their life cycle. Effective and efficient processing of such data by humans is practically impossible. Therefore, we are looking for the possibility of using machines that will independently select and collect information operating according to the manager's specific patterns and goals. For this, however, a long training process is required for the algorithm to be effective and avoid predictable errors. According to the assumptions of artificial intelligence, the difference between machine learning and artificial intelligence should have the ability to create new works, new art, including the ability to recognize images and sounds. Machine learning can also create, but always based on the analysis of the acquired data and previous research results, or by prioritizing a data set into groups of records with similar characteristics. It is called clustering. It can be seen that we are still far from achieving the original concept of artificial intelligence. Here we see an example of neural network architecture used to predict the value of bending moments caused by pre-stressing tendons in a double-girder post-tension concrete bridge. Here we see the input layer, hidden layers, and output layer. Together they build a network architecture. In this case, a single hidden layer of 15 neurons was used. The algorithm's operation is based on the random generation of the indicated number of vectors created from a set of parameters describing the geometry of the tendons. By going through selection, crossing, and mutation, successive generations of vectors were created. You can see the set of solutions analyzed in the initial generation of the 50th iteration. In subsequent iterations, the algorithm systematically selected and organized solutions, aiming at the optimal tendon system. Practical applications of artificial intelligence in construction may include such issues as optimization tasks. It can be in designing, management, in the life cycle analysis, automatic classification of registration data and inspection results, pattern recognition, I mean speech or written text, predicting trends in structural degradation models, control of autonomous machines, navigation in an unknown area of the construction site, expert systems and decision support, and finally damage detection in monitoring system. We will now jump to issues related to the management of construction processes. First, there will be a lean construction. Lean construction is the adaptation of lean manufacturing or lean management philosophy to improve the design and construction process. The prototype of lean construction is primarily the strategy of the Toyota production system. It is a business management concept that developed at Toyota mainly in 1960s and 70s. But thanks to organizational solutions developed even since in 1940s, Toyota produced high-quality cars using far fewer resources than its competitors. Over time, Toyota's solutions began to be copied by other Japanese car manufacturers such as Daihatsu, Mazda, and Nissan. At the turn of the century, the advantages of this approach were noticed worldwide and introduced in the production of cars in the United States and Western Europe, and then also in other sectors of the economy and even in entities from non-productive sectors, especially in services, logistics, and even at airports and offices. Here we have 5 basic principles of lean management. The first is defining value for the customer, like what the customer perceives as the product's value or service. The value for customers is, among others, quality, functionality, price, appearance, availability in a given place and time, additional services, and time delivery. Then we have to identify the value stream and all activities in this stream. The production and delivery of a product or service to the customer requires the performance of the many interrelated activities and operations. Activities that do not add value must be eliminated. We must have a continuous flow. It consists of producing a product or providing a service as smoothly as possible, enabling a single product, a batch of products or service to quickly move through the various stages of their production without disruptions, interruptions, and downtime. Then is the pooling system. Products and services should be delivered to the customer by his needs. An example, exactly when they are needed or exactly in quantity they are needed. And the last rule is the pursuit of excellence. This is a rule and condition for maintaining and the introduced improvements in the continuous improvement of all organization processes. This philosophy allows us to achieve higher and higher profits thanks to self-improvement aimed at customer needs. Enterprises, companies operating according to these principles are companies focused on creating maximum value for the client using minimal resources thanks to well-organized processes. And BIM is used for modeling and process management, but just in construction works. Such opportunities are provided primarily by the use of employees' talent and every level of the organization. This approach to production processes is based on flexibility, high quality, and elimination of waste and continuous improvement. When adapting to construction, it was assumed that construction was a specific production process based mainly on the design. This approach tries to manage and improve construction processes while minimizing their cost, while maximizing the effects and considering customer needs. In construction processes, we can distinguish the following examples of waste. It can be overproduction, when we design or build too much ahead of time without demand from the next process or more than needed at a given stage of the project. Unnecessary activities. Any unnecessary effort made by a designer, construction site worker, or equipment, usually the result of the improper organization of work and lack of standards. Downtime, that are long periods of inactivity of people, machines, or materials in the design construction process. Unnecessary transport, unnecessary movement of materials and people and equipment. Excessive inventory, more than the necessary minimum amount of materials or equipment and even staff. Defects, that are all collisions and errors in the design, quality, and events on the construction site, including failures, catastrophes, complaints, and warranty repairs. And finally, excessive processing. That's any activity that is not necessary to design or build an object, taking into account the client's parameters and quality level. Each entity involved in the project, which is implemented by the philosophy of lean construction, from designers, contractors and subcontractors, manufacturers and suppliers, the client, and supervision, is taken into account to ensure the highest quality of construction project with the shortest possible implementation time and as low cost as possible. Also environmental and social. The tools supporting this philosophy are both BIM and VDC technique discussed below, which is, in short, consists of virtual object design and construction simulation. They enable not only process optimization, but also effective cooperation between participants in the construction process. The BIM methodology influences linear construction processes as it directly impacts the way contractors, subcontractors and suppliers work. Access to the highest quality design information with eliminated errors thanks to the analysis of the virtual structure allows, for example, to perform a trial virtual assembly in the case of higher degree of prefabrication. And this is the tendency today. This translates directly into reduction in construction time. BIM models are useful not only for finding design conflicts. Shared models, which are linked to planned assembly sequences, make it possible to analyze the interdependencies between different processes, especially deliveries. The key assumption of lean construction is careful production and supply planning, and it's every week. This allows us to search for activities that may not be possible to complete correctly and completely. Therefore, identifying any physical, logical, or organizational conflicts by virtual construction in a BIM environment improves the stability of workflow and resources. The ability to coordinate activities on the construction site with the entire team at every level and in various industries is improved. This enables shorter time buffers between processes and teams. In turn, reducing the time needed for actual production and delivery allows manufacturers to reconfigure their deliveries. It will no longer be just-in-time deliveries, but just-in-time production. This reduces the required component in inventories and associated waste. The costs of storage, multiple handling, damaged or lost parts, transport coordination, etc. are reduced. This is due to the fact that BIM tools allow you to generate reliable and accurate workshop drawings, also in the critical final stages of investment implementation. In the case of such a late changes, manufacturers may be more sensitive to customer needs. The lean construction philosophy affects not only the operation of construction companies, but more and more often also the public sector. It is mainly about a new look at the services provided by public institutions. Budgets and public resources are constantly reduced while the needs and expectations of societies grow. Therefore, the public sector must learn to use its increasingly scarce resources more efficiently. This is especially true of infrastructure maintenance. Another element in the field of management is the integrated project delivery. Integrated project delivery is a certain concept for the implementation of a construction project, the main assumption of which is the integration of people, systems, organizations, and business activities in the construction process, which uses the skills, experience, and knowledge of all members of the implementation team to the greatest extent possible. This is done while minimizing waste and unnecessary expenditure and optimizing efficiency in all design and construction phases. The concept, however, is not entirely new. After all, the concept of a general contractor did not exist in the past. There were also non-distinctions between architects and builders. Today we would say structural or civil engineers. The construction masters were fully responsible for the design and used technology to construct the building. The separation of these functions took place at the turn of the 18th and 19th centuries, and it became permanent with the Industrial Revolution. Over time, has led to barriers and misunderstanding between architects, engineers, contractors, and investors. We can observe it today mainly in the most traditional investment process model, which is the separation of design from execution, from construction, and conducting them in a separate contract: design, bid, build. There are three basic models for the implementation of construction investments in the construction industry. Of course, many more can be distinguished, but usually they are a certain modification of the three visible in these diagrams. They show the relations between the participants of the investment process, especially between the ordering party, the client, and designer, general contractor, and subcontractors and suppliers. So we have a design build model, and the new concept of an integrated process. The first is the model called build in Poland, design bid build in English. The client independently hires a designer first, and then a contractor implements the design documentation prepared in advance. This is actually accompanied by a lack of trust and a power struggle between the three main parties of the undertaking from the very beginning. Sharing information in such a system causes exposure to various threats and lowering your position. Lawyers and insurers quickly come to this arrangement and take advantage of any misunderstandings and conflicts. As they are not directly involved in the investment process, thus increasing its costs and extending the implementation time. In this system of investment execution, BIM gives the least obvious benefits. The second model for implementing construction investments, called design build, is based on the fact that design and construction services are performed by one entity which receives a comprehensive order from the client. This allows the client to minimize risks, reduce construction costs, and shorten delivery times by overlapping the design and implementation phases. This allows us to eliminate some of the disadvantages of the previous model. This system allows the contractor to carry out his works while maintaining great freedom and flexibility, using the most convenient design and technological solutions. This allows him to optimize construction costs. Here, BIM models prove themselves better as they improve cooperation between the designer and the contractor from the beginning of the contract, especially since the relations and arrangements between the designer and the contractor no longer concern the client directly. However, this places the general contractor in a highly privileged position about the designer. Besides, there is a risk of not a very precise description of the client requirements, which may reduce the quality and durability of the building, especially when we strive to optimize construction costs without looking at the effects it may have in the building's subsequent life cycles, especially in maintenance. Despite these drawbacks, this model has been launched more and more frequently for some time, especially in the public sector, which aims to transfer as much risk as possible to the service provider. With the development of BIM technology and greater opportunities for information exchange between partners in the construction process, new investment implementation models also appeared. The models discussed earlier assumed depending barriers between the parties, which actually began to lose sight of the main goal, which is just to build the best facility, the best building for the client. Of course, it is no longer possible to go back to the Renaissance, but modern tools, mainly BIM and various platforms to exchange digital data, create new opportunities. After all, it is possible to prepare a multilateral agreement between key actors in the process. They all implement a single agreement that defines their respective roles, rights, obligations, and others. As a result, this multilateral agreement creates a temporary, virtual, and in some cases even formal organization for the implementation of a specific project. Since there is no one joint agreement, each party understands its role concerning the other participants. Multilateral agreements require trust because the compensations they are right are linked to the project's overall success, and individual success depends on the contribution of all team members. The contract also includes protocols covering the exchange of information and sharing both risk and profit among individual participants. This is what integrated project delivery is all about. All participants of the project conducted by this philosophy, like investors, consultants, designers, general contractors, and subcontractors, should follow the following rules. Mutual respect and trust. Participants understand the value of cooperation and are obliged to work together as one team for the good of the project. Then mutual benefit, rewarding everyone according to the degree of their involvement with fair risk sharing. Early definition of the goal. Project goals are developed and agreed upon as early as possible. Early involvement of key participants. This improves the decision-making process and thus significantly speeds up the implementation. Clearly defined standards and open communication. Disputes are identified when they occur and are quickly resolved. High efficiency. Joint efforts are made to optimize design solutions, the decision-making process is improved, and the number of changes at the later stages of the project implementation is limited. Um, Use of appropriate technologies. Well, technologies should be as functional, universal, and interoperable as possible. And finally, organization and leadership. Well, leadership is taken by those team members who have the best competences in a given field, and all roles should be defined at the beginning of the work. This approach promotes a high degree of communication and intense cooperation between partners in a construction project. Not only the risk is shared, but the profits as well. Better collaboration can therefore result in additional benefits for all team members. These benefits can help teams overcome the relationship difficulties of the design-build model we discussed earlier. Now, they are all in the same boat, and everyone has incentive to work together. IPD also works in other ways by rewarding innovation, not just encouraging innovation. The whole team wants to create new value by selecting the best solutions, materials, and technologies for the project. However, adopting IPD as a standard for cooperation in construction projects poses some problems. As most construction projects involve various stakeholders, traditional IT solutions may no longer be sufficient. The large size of emails, attachments, variety of file formats, data and resource security, high software costs, additional staff competencies, all these are driving the development of technology for online collaboration in the construction industry. It is no longer just BIM, but dedicated software that improves the flow of documentation and communication so that everyone works on the same project, on one project. Such tools are the previously described CDE, Common Data Exchange environment or platforms. Building lifecycle appear very often in my lectures. Now we will define them a bit more precisely. The 2019 report of International Energy Agency indicates that nearly 40% of global energy consumption is consumed by industry, mainly steel, cement, aluminum production, and the chemical, petrochemical, and paper industries. Such a high energy consumption contributes to direct carbon dioxide, CO2 emissions, estimated at 1/4 worldwide, which many experts believe may impact the environment in the context of climate change. Although I admit that this topic has become very politicized and it's a bit more like professing a new religion today. ideology and faith are more important than common sense and openness to other views. In the case of these basic materials, they are the largest customer in the construction industry. More than half of the steel produced in the world is used to construct buildings and infrastructure. China's enormous steel needs, more than 40% of global demand, have pushed up the price of this raw material and pushed it towards greater use of concrete and thus the demand for cement. Meanwhile, cement, which is already the construction domain, has a substantial share in CO2 emissions. That is why many research centers are currently working on reducing the energy consumption of cement, for example, by using alternative fuels and extending the life cycle of design and existing facilities. Economic development is always accompanied by a growing demand for building materials and an increase in energy consumption. Of course, a side effect is the emission of greenhouse gases, which mainly include CO2. Since 1971, the production of cement has increased almost sevenfold and steel production threefold. Over the same period, the population doubled and gross domestic product nearly fivefold. The production of cement and steel is expected to increase by 10% and 30% by 2050. The conflict between economic needs and environmental protection and available resources is being perceived more and more. This forces many industries to change technology and improve the efficiency of production and use of basic building materials. They fit into the new economic doctrine called sustainable development. The philosophy of sustainable development largely consists of managing the current resources in such a way as not to reduce the chances of future generations to meet their needs. Its basic elements are environmental, economic, and social aspects that interpenetrate and influence each other. For each of us, the natural environment is the basis, while the economy is a tool for us to achieve prosperity and social acceptance. For business, including construction, it is important for sustainability to take a holistic perspective and understand its short and long-term effects. Therefore, thinking about the product or service life cycle has become a useful tool for sustainable development. This differs from conventional business practices that have focused on more immediate factors such as cost, quality, and availability in the supply chain. Life cycle considerations still include these factors, but from a lifetime perspective. This especially applies to decommissioning and disposal costs, which is of great importance for the natural environment, which is, after all, one of the fundamental pillars of the philosophy of sustainable development. Thinking about life cycle in a business context starts with considering the impact of raw material extraction and other needs input right at the design stage. Then the transport of basic materials, the organization of production and execution processes, and their impact on the product's usability are taken into account. In the next steps, the distribution and use of the product are considered until its final disposal. Each stage of the life cycle focuses on inputs and outputs in raw materials and waste. Such an approach appeared as early in the 1960s, when it was first used to consider the economic costs associated with various energy technologies and the accompanying emission of harmful substances to the environment. The life cycle concept initially evolved as a sophisticated method for assessing industrial products' environment and social impacts. Over time, it also found its way to construction sector, where it may soon be a key importance when assessing many investment activities. With the entry into force of the new Act, the criteria for selecting the best offer during the tender have been extended. These new criteria include determining the cost criterion using the life cycle accounting, after-sales service, which may apply to the procurement of construction services, in particular the method of implementing the investment in the design, build, operate, maintain mode, environmental aspects aimed at meeting the levels of environmental and climate impact set by the contracting authority, and finally, social aspects based on taking user needs into account. A comprehensive assessment of investment activities, which would be consistent with the assumption of sustainable development, should take into account the economic and environmental aspects of the life cycle of the planned building and social conditions. This approach is used in the so-called integrated life cycle analysis, which includes the assessment of economic, that's the life cycle costs, environmental life cycle analysis, and social life cycle assessment. All the components of integrated life cycle analysis help project stakeholders make informed decisions early in building and construction. Unfortunately, not all of them already have the appropriate codification and development level that would allow their widespread use. There is also no one universal indicator that would simultaneously express the profitability of venture, taking into account these three types of analysis. The most common aspects of sustainable development included in the integrated analysis are shown in this table. They result to the economy, the environment, and society in turn. Each of these aspects should be duly taken into account when planning a new facility and assessing the existing one in terms of its further use. Such analysis should be carried out in the most balanced way possible, considering as many issues as possible and aiming to minimize negative effects and maximize positive outcomes. The beginnings of economic analysis of the life cycle cost product uh, date back to the first half of the 20th century. However, their most intensive development took place in the turn of 70s and 80s when they were widely used in the armaments industry, military industry, especially in machines and aeroplanes. Calculations of this type are used to assess economic dependencies describing long-term used products, devices, or objects. They are very often procured and operated by public institutions for which planning, transparency, and cost effectiveness are of key importance, especially since in this type of investments, the initial cost, called capex, capital expenditures, are often only a fraction of the actual expenses incurred during the object's operations, which is called OPEX. For this reason, many countries began to look for methods to improve the management of resources that would be used to operate and maintain the facility during its sometimes several dozen year life cycles. In the LCC analysis, components of the object life cycle are distinguished, which relate to three collective entities related to analyzed object. These entities include agencies, uh, that's the unit which is responsible for the investment, like for example, National Road Administration or Railway Administration, whose participation in the life cycle consists of covering the financial expenses related to the bridges design, construction, maintenance, and demolition. Then we have user. It is each beneficiary of the investment which bears the costs of using the resulting object, building or bridge. These may be the costs of vehicle operation and losses related to traffic obstructions or speed limitations caused by deterioration of the facilities, technical condition, or detours during the renovation of the structure. And finally, we have society. It is a unit that incurs costs other than the construction and maintenance of the facility itself. This may be the facility's environmental impact, subjective aesthetic and historical values, or, for example, medical services for accidents on a bridge. There are several computational approaches in LCC analysis that, to varying degrees, cover the various components of the facility's total cost balance. In this diagram, I showed the approach presented in the ISO 15686 standard. In charging the property for costs, it ignores the user and the public, focusing solely on the facilities agency. It also doesn't take into account the private elements of profit that are important for the project. Simultaneously, it makes it impossible to carry out an analysis that is important in making decisions. It is about, for example, determining the benefit to cost ratio analysis. This simplification of the calculations is due to the clear predominance of expenditure by the agency. Therefore, often only costs related to the entity ordering and the object are taken into account. The calculations results are directly correlated with the time course of the facility life cycle and the occurrence of individual cost-generating events. Such events are successive occurring, construction of the facility, its annual maintenance costs, single repair, rehabilitation of the entire facility, and its liquidation. The key elements influencing the facility's total cost are the costs of its construction and demolition, and length of its life cycle and the related frequency and amount of expenditure incurred on its repair and continuous maintenance. In addition to the above-mentioned variables related to the structure in terms of construction processes, many economic factors treat the facility as investment that affect the analysis final result. These factors are primarily macroeconomic elements such as inflation processes or changes in exchange rates, which directly impact the discount rate describing the current value of the investment. It is about converting to the net present value of money. Although many economic factors influence it, it maintains a relatively stable value which fluctuates around 5% of investment costs. The calculated value is the value reduced by the inflation rate. Other factors influencing the economic situation, such as economic or inflationary crises, are not considered in the analysis due to difficulties in forecasting them. The economic life cycle analysis is the most advanced comparing the rest aspects. Undoubtedly, this was due to the Public Procurement Directive and the resulting amendment to Polish law. These documents made it possible to use LCC and tender procedures. Their consequence is the publication in 2018 of a regulation important for the construction industry on the method of calculating the life cycle costs of buildings and the method of presenting information on these costs, providing the necessary formulas and parameters. It defines a building life cycle and all linked costs like purchase, operating, maintenance, and demolition costs. According to the audience, uh, the life cycle cost of a building should be calculated as the sum of the mentioned above costs using the simple formula provided here. For the client, the purchase costs constitute the price from the offer, while the operating costs are related to the expected energy and water consumption in the calculation period. As for the entire building's maintenance costs, in the same calculation period, the unit maintenance cost of each product, each building element, are summed up with the value being reduced. The unit cost of maintaining a product results from its replacement cost and the number of cycles expected for in the calculation period. This number of cycles is specified in the annex to the regulation where, for example, the windows have 1 to 4 cycles and the elevation has 1 or 2 cycles. This approach enables the contracting authority to make its investment decisions more consciously and correctly. It is not only the short-term criteria, for example, the acquisition cost, the purchase cost, called capex, that decide. This approach is often presented in the form of the so-called iceberg syndrome, where the investor only notices the initial costs. On the other hand, the costs of ownership, for example, use and maintenance, which are in OPEX, hidden at this stage, are overlooked or underestimated. Meanwhile, then can be as much as 70% of total costs, which are called total expenditure or otherwise TOTEX. The beginnings of environmental analysis date back to the great fuel crisis at the turn of the 1960s and 1970s. Initially, it was mainly about the most economical use of the increasing hard-to-reach material in industrial production. Currently, these are standardized calculations methods described by the ISO 14040 series of standards. From the practical point of view, despite the previous interest, mainly in private enterprises, they are now carried out most often by public organizations, especially in projects related to green energy. Its application to building structures is not yet widespread. LCA analyses are based on an object life cycle calculation, but the cycle is slightly more extensive. Instead of monitoring cash flow, it focuses on monitoring energy demand and emissions of harmful substances from the moment the raw material is obtained to the used product's disposal. We can see this cycle in this diagram. The LCA methodology is divided into three basic components that are interpreted in parallel with each other. It should be noted that it is an iterative process. The first component is to define the purpose and scope of the study, along with the assessment categories taken into account. This is important because even a small change in the input data can seriously affect the analysis results. In practice, when analyzing public entities, the aim is usually to determine the total greenhouse gas emissions expressed in kilograms of CO2 equivalent and possibly the emission of other harmful substances and energy demand. On this basis, a comparative analysis is then performed. As the study scope, the time and space on which the facility will operate by the assumptions provided by the contracting entity are selected. The second LCA element is the analysis of the lifecycle inventory dataset selected from the general list in the first part. The main task here is to define the LCA component processes for a given object. We have seen these components over the object's lifecycle in a simplified way in the diagrams shown a moment ago. Still, it is superficial approach, hardly approximating the actual number of processes and necessary to consider the variables that occur in the life cycle of the building. To obtain the most accurate results of the analysis, the goal is to divide the entire life cycle of the object into a set of unit processes, as in this diagram. However, it is currently impossible in practice due to insufficient documented emission data related to individual processes. Instead, the emission estimation methods are based on the use of data on material with similar parameters. The accuracy of this approach is unfortunately very debatable. The last third part of the method is the life cycle impact assessment. It is nothing other than comparing the data from the set analysis results to the previously assumed criteria and the object that the object doesn't exceed the predetermined maximum values of inflows. The data derived from the previous stages of the analysis are called eco-profile and subject to interpretation. The impact assessment categories already mentioned above differ from LCA studies. The problem of assigning weights to the elements of the analysis is still unsolved. In general terms, this part concludes the considerations of on assessing the impact on the structure being the starting point for conducting integrated analysis. Similar to the LCC, of course. Uh, it should be noted that a much greater number of variables characterized by LCA analysis compared to LCC, which means that the results of these calculations are characterized by high uncertainty. In the case of LCC analysis, only the cost of the investment lifecycle stages were the variables. However, in the case of LCI analysis, apart from the passage of time, the stage's total emissivity should be considered, which consists of many more factors than expenses incurred for a given element. Although there are studies on the level of emissivity of the building material produced, like steel production, there are still too few of them to the huge variety of materials and technologies used in construction. Chronologically, it is the youngest part of the integrated life cycle analysis and then therefore the least developed. In the 1990s, it was introduced as a supplement to the LCA analysis concerning social issues. The discussion on its general shape, variables, and indicators seriously began around 2003. The first indicators included were employment, salary, and positive and negative health effects on investments. For this purpose, international research and experience covering various industrial sectors and the public, academic, and economic sectors were used, which were carried out under the United Nations Environment Programme. Unfortunately, these guidelines do not allow for a meaningful analysis. They only provide a certain computational tool that will outline information about the product or investment's social impact without deciding on its actual usefulness or profitable. The social part analysis consists mainly of checking whether the principles of ensuring social welfare and sustainable development policy are not violated in the product life cycle. In principle, these criteria relate to the impact of investment on people, their well-being, cultural heritage, and social behavior, referring to basic factors, living and working conditions. Currently, the social analysis is the least formalized of the methods described above and is not legally required in any country. Due to the lack of codification and low demand, The development of work is slow, meaning that social analysis is most often omitted in integrated analysis. The life cycle analysis described earlier may be useful as a tool supporting decision making according to the philosophy of sustainable development only when used simultaneously in the form of the so-called integrated analysis. However, the scope and sense of integration should always be determined by the investor's need. Therefore, in many typical small objects, like small buildings, culverts, it will rarely be necessary to carry out complex environmental, let alone social, calculations. However, for larger bridges, larger facilities, mega projects, where different design and execution variants are considered, an integrated analysis may already be justified. Such integration is possible in the three ways. First, introduction of LCA and social analysis to common costs as a part of cost analysis. Second, calculating the score in points with weights. And third, calculating the score in points and weights, but limiting the maximum value of the analysis part. As you can see here, mathematically, the integration of LCC and LCA analysis is not difficult, but the issue is still open. The last management issue is asset management. Managing resources or asset management is a combination of knowledge about finance, economy, engineering, and other practices applied to physical assets, particularly the management processes themselves. When describing resource or asset management, English language terms are often used, dominated by the two terms, asset management and facility management, which will be explained soon. Both AM and FM are used to provide the best service level and the reduction and cost associated with using existing assets or resources. Uh, Infrastructural and specific buildings, such as hotel or office buildings. From a time perspective, asset management covers managing the entire life cycle of individual assets. Thus, it considers successive and, in some cases, repetitive processes such as design, construction, commissioning, operation, maintenance, repair, modification, replacement, or decommissioning of physical and infrastructure assets. With the manager's usually limited budget, the operation and maintenance of assets require the adoption of some prioritization mechanism for spending funds. Infrastructure resource management in the 21st century has become as critical field in most developed countries. This is because the network of various infrastructure in these countries, like roads, railways, energy, telecommunication, etc., was already fully built in the 20th century. Therefore, the basic task of the owners of these networks is now to manage them effectively. Uh, we can use the asset management system standard described in the ISO 55000. They define the terminology, requirements, and guidelines for implementing, maintaining, and improving an effective asset management system, regardless of the nature of these assets or their owners. Asset management in any organization, like road or rail administration, must begin with understanding and defining the organization's purpose and context. Another crucial step is identifying the set of assets. They are defined as a set of resources that an organization uses and consumes in producing and providing services. These assets are located in individual units or divisions of the organization and may include elements of the technical infrastructure presented, for example, in this diagram. The indicated selected assets could be grouped in various ways. It will depend on the specifics and mission of organization. This diagram shows a possible grouping example, dividing them into technical assets, consumables and knowledge, human and financial assets. Over the last few decades, and especially after the advent of BIM, we can observe the interpenetration of the two concepts of asset management. Uh, AM, more generally as assets, and FM, more specifically as objects. The main differences between them are the type of assets managed and the resulting required methods. AM is already properly standardized in ISO 55000, and FM has its own standard in the form of ISO 41011 standard. Three main areas define AM and FM's differences: asset types, management objectives, and operating methods with responsibilities. Asset management is defined as a firm's effort to identify and maintain a certain level of value for all its assets. They can be both tangible or intangible. Facility management is limited to physical assets that are used and support the day-to-day operations of the company. The priority is to improve the company's productivity and efficiency. There are two basic types of assets: real estate, like buildings, factories, apartments, offices, infrastructure, bridges, etc., and movable property. I mean, items that are not permanently connected to real estate, like plant equipment, machinery, tools, devices, vehicles, etc. The main goal of asset management is to maximize the return on the assets of the organization. The priority is to improve maintenance efficiency and improve reliability. The asset manager is usually not concerned with the operating costs associated with the assets. A facility manager's main goal is to provide an optimal working environment and improve the company's overall performance. Therefore, facility management focuses on the needs and the requirements of employees while optimizing operating costs. This is the key difference between AM and FM targets. The main task of AM is to ensure the effectiveness and efficiency of all processes in an organization. In AM, there is usually no management or direct leadership of the staff involved in resource maintenance. On the other hand, FM should provide a variety of support services to its customers and end users and suppliers and contractors. The activities of both AM and FM aim to improve the organization's return on capital, but differently. AM by asset maintenance and reliability management, and FM by overall service and end user management. So it can be seen that AM and FM are areas of interpenetrating activities involving the management of different types of resources. For this reason, they are often used interchangeably, although there are differences. FM focuses on physical rather than cubiture buildings, while AM has a wider range of applications. Both generated their own standard or specifications, and both developed their own language of preferred and defined terms. This is shown in this figure here. FM can be considered as a part of, or even an M2, because AM goes beyond FM, providing a more comprehensive approach and the context of impact. So, how can the BIM methodology be used in the management of infrastructure resources, which is, after all, a priority task for most organizations that play the role of road and rail administration? Uh, BIM is a method of managing information throughout the life cycle of a structure and, therefore, of an organization's constructed assets. It supports the creation of these assets, models, provides data on their properties and values, facilitates the exchange and visualization through the use of digital tools and intelligent object-oriented data structures. This helps to avoid the loss of information when moving between the different stages of the life cycle and transferring responsibilities related to resource management, like commissioning of the constructed facility, change of manager, etc. So, if the information is the most important thing for BIM, and not just three-dimensional models, how to use it to maintain the quality of our roads, our bridges, buildings, safety, and optimize operating costs. The basis should undoubtedly be the existing and proven standards for asset management, ISO 55000 and ISO 41011 series. BIM, with its standards, is not meant to replace them. With its more and more developed models, with which information should be integrally related, BIM has a chance to become a great tool that can be used in the resource in the asset management process. These resources can finally have their digital counterpart in the form of a virtual model. This model can be used to store information about an asset and simulate various processes, like maintenance or degradation. It can be a kind of digital twin of a real asset. The question is, on roads, do these digital twins have to look like a true three-dimensional copy of our highway? Well, not at all. And even in many cases, it would be downright disadvantageous. This is where the ISO 19650 series of standards comes in handy. They primarily define how building data is organized and digitized in their individual life cycle stages, not the requirements for the appearance of the models themselves. The B model can be simplified in its representation. However, it must contain all the information needed at a given stage. Therefore, it is enough that the data on the technical condition of the road collected during the maintenance process will be linked to its simple linear model. There is no need to jam servers with unnecessary data describing just the details of a 3D model, which doesn't mean that they will not be supplemented in this way in the future. An example of such a road information model is shown in this figure. These relationships are clearly seen in this figure from ISO 1960 650. The key abbreviation in this figure mean asset information model and project information model, which were already described in my previous lectures. Point A, it's the beginning of the project delivery phase and passing the relevant information to project information model, of course, if the facility is designed as a new, or from asset information model to project information model if the object and model already exists, for example, during reconstruction or replacement. Point B is a gradual development of the model with design assumptions into a virtual as-built model. Point C, it's a model delivery completion phase during final acceptance. Um, it needs transfer of relevant information from project to asset information model. Point D, operational phase and excessive updating of the asset information model. And finally, point E, it's significant that are significant events in the life cycle, like renovations, reconstructions, that force a larger update of asset information model. Structural health monitoring is also related to asset management systems because it concerns monitoring the technical conditions of structures in their life cycle. Structural health monitoring mm, is currently one of the necessary elements that should be equipped with intelligent, another way, smart technical devices, structures, or facilities. There is a talk of intelligent buildings like smart house, smart bridges, and even smart cities. In some simplification, it can be said that their so-called intelligent structure should be equipped with a network of various sensors that record changes taking place in the monitored object on an ongoing basis. The results of these observations are forwarded to analytical and expert systems, where after processing, often in real time, decisions are made regarding specific reactions of the entire system or remedial actions. SHM monitoring is particularly often used in critical infrastructure facilities where unexpected failures can cause significant losses and difficulties. They also include bridge structures, especially those located over large obstacles, rivers, and in the area of the critical road or railway junctions, and located on unstable ground, like post-mining, karst, seismic areas. The data obtained by these systems can be used to develop a strategy to optimize maintenance costs, improve efficiency and quality, and verifying the correctness, effectiveness, and durability of structural solutions proposed by the designer. Basically, however, SHM monitoring is used to detect and assess the impact of damage of the monitored structure's safety. Damage is defined as changes in the structural system's material or geometric properties that may reduce the performance of an object or lead to its shutdown. Most often, monitoring covers objects with large spans in responsible locations with prototype solutions or building areas that pose additional threats and risks, like typhoon or earthquake zones. For this reason, most bridge structures with installed SHM monitoring systems are located in the Asia and North America. The first monitoring systems on Polish bridges began to be installed after year 2000. Currently, over a dozen bridges are equipped with SHM monitoring. Here we see selected examples from Kraków, Płock, Puławy, and Wrocław. Certainly, there will be more and more such examples. Monitoring systems usually generate large amounts of raw data, which are of little use directly and without processing. Therefore, they must be properly processed and organized to make them easily accessible and legible. These facilities their better interpretation, analysis, and decision making. Since the BIM model is usually built of 3D components, which allow them to be associated with a variety of information, they can also be used to describe various types of accompanying phenomena, also those related to the monitoring of changes in the technical condition. The open IFC format related to BIM can also be used to describe SHM systems. The description of individual sensors using IFC is relatively simple, as shown by the example of the visualization of the reinforcement concrete beam in our laboratory. We prepared it for the experiments of our PhD student from Bangladesh. He used a string and acoustic sensors to detect cracks in the concrete. A more global approach to monitoring large bridge structures is the use of satellite observation. Italian engineers, in collaboration with NASA's Jet Propulsion Laboratory, analyzed satellite images of the Morandi Bridge, the tragic collapse of which in August 2018 is considered one of the greatest modern construction disasters. For this purpose, radar images from 4 satellites of the Cosmos SkyMet program in the Italian Space Agency and other observation satellites from the Sentinel program of the European Space Agency were used. The INSAR, interferometric synthetic aperture radar technique, used in this case uh, to obtain information on relative altitude data by analyzing the phase differences of radar signals from 2 microwave observations of the same area at different times. It turned out that the changes in the grade line of the road near the later collapsed pylon were already visible in 2015. Besides, between March 2017 and August 2018, there was a significant increase in structural changes in several bridge parts, indicating that at least part of the structure was already in a critical condition. Undoubtedly, the shown directions of BIM models, integration with SHM systems and GIS systems, are auspicious. Uh, this is one way of practical implementation of the idea of the 7 dimensions in BIM models. The assumptions of the BIM 7D model are to be used in the process of managing objects in their life cycle. Additionally, equipped with elements of the SHM model with access to databases with recorded monitoring results and supplemented with analytical tools. It will serve almost as a digital twin of the actual structure. And so we got to the last issue today, which are digital twins, which, as I showed, are naturally related to structural health monitoring systems. I've already shown these pictures. Uh, they make us realize how little has changed in our construction industry. Meanwhile, people already landed on the moon more than 50 years ago, and they even happily returned from there. Well, it was during the Apollo program that the concept of a real object twin appeared for the first time, though certainly not a digital twin yet. At that time, the rocket sent into the space had its counterpart in the form of a model that in the 1960s had no right to resemble the models commonly used today in virtual reality. Not only the space industry today has its digital twins, but also planes, cars, oil rigs, and even bicycles. This approach is also already used in construction. We know the so-called smart houses, smart cities, our motorways, which will be driven by autonomous cars, will have to change in future. The railway infrastructure is also changing. Modern possibilities in terms of computing power, data structures, and algorithms efficiency have allowed for the creation of a new concept of a digital twin, by some also referred to as a digital shadow. It is a digital or virtual model of devices, processes, and even people. Machine learning and artificial intelligence algorithms are used to build data twins, which allows for a dynamic digital representation of its physical prototypes. This would not be possible without complex sensory systems that record internal and external influences on a physical object. In this way, the knowledge base about a given object is constantly improved, which may also come from the machine's previous applications or the assessment of the behavior of living organisms. Currently, digital twins are most often used to simulate the operation of wind turbines or aircraft engines. It uses this technology to create virtual models to monitor and diagnose physical assets, optimize performance, and forecast performance and sustainability. The concept of the digital twin has been mono-emphasized in the Industry 4.0 strategy. The general idea of a digital twin is to create a replica of physical object in an information model, taking into account its life cycle as complete as possible. This requires a fairly detailed specification of the physical prototype with documented changes and accompanying processes. Therefore, data from the history of the system or device and information from experts are used. The digital twin can be used to report on the technical condition of its physical counterpart. When properly configured, it also serves as a model to perform calculations and create scenarios of the entire system to optimize time or costs. The development and more common use of digital twins results from the interdisciplinary approach to engineering and the achievements of IT techniques, which can include assimilation of diverse data structures, machine learning, high level efficiency, and real time simulations, possibilities of process visualization, etc. This technology also shapes an individual version of the Internet of Things, where physical objects can live and interact with practically other machines and people. In this context, they are referred to as cyber objects or digital avatars. And the digital twin can also be part of the concept of a cyber physical system. These issues are related to the previously described industrial development strategy and the fourth industrial revolution, particularly to the implementation of an intelligent factory in which cyber physical systems control physical processes. More and more examples describing this type of complex objects can be found in the literature. For example, it is a steel mill where the digital twin can make decisions even when the connection to the physical counterpart fails. Now I'll present some more examples and possibilities of using digital twins. Designers will be able to use multidisciplinary digital models that will enable complex and interdisciplinary simulations. Currently, such activities require separate models and independent development environments. The integration of these models in the form of a digital twin will allow for a quick and inexpensive prototyping of new projects, with the possibility of inventing even a future user who doesn't have to be an engineer. The simulation may concern the model's response to various influences and extortions such as static and dynamic loads, noise, environmental influences, human interactions, lighting, etc. According to the current demand on the construction side, real-time inventory tracking and delivery automation can also have their digital twin. These are also known examples of traffic control in cities or relatively simple solutions of municipal parking networks that suggest the location of free spaces. Linking digital models with the increasingly used technical condition monitoring, that's another issue. Digital twins may be the next step in the development of SHM systems discussed above. They will enable operators to react quickly and reduce the risk of difficulties and threats. In these solutions, machine learning can be used to predict and detect anomalies, and autonomous decision algorithms can be introduced, thus eliminating potential human errors. Digital twins can help manage infrastructure resources. These issues are described in more detail below. Uh, Only here it can be noticed that the integration of the asset management needs, electronic resource registers, and the processes of degradation or improvement of their condition, development of the knowledge base about resources, and processing of data collected during inspections or from monitoring systems can be implemented in the form of the digital twin. It can thus simulate a certain defined network of road or rail infrastructure object or building, even the city. As such a twin matures, we can optimize the network's operation, adapting to various scenarios. This will make it easier for managers to make decisions in planning maintenance activities and determine the budget for the operation, renovation, or replacement of facilities. Different models of the digital twin can arise and become related to each other. So we can have a digital BIM model called digital twin model, and another in the form of a model created using reverse engineering tools. In this case, it was a reconstruction using photogrammetry and laser scanning methods. This model is called a reality twin model because thanks to the cyclical repetition of the reconstruction procedure, it is possible to capture the current state of the 3D geometry of the structure and the properties of the surface structure of the components of the object of the bridge. The results of each subsequent reconstruction are compared with the last version of RTM model. On this basis, an automatic report is created containing the identified differences that may suggest damage. Besides these, models must be supplemented with a FEM analytical model, which is used to assess the impact of the damage found on the structure's load-bearing capacity and other performance properties. For example, if defect, degradation, or discontinuities of the material, like cracks, are identified, the parameters of the FEM model are changed by reducing the moment of inertia, changing the elastic modulus, or introducing specific non-linearities. The big challenge is to integrate different formats and types of data from different sources and devices. This can be, for example, reports from traditional visual inspections or with the use of drones, geodetic measurements, visible and hyperspectral imaging, point clouds obtained as a result of laser scanning or photogrammetry, data from satellite observations in the form of interferometric radar images, measurements results from SHM monitoring systems, and even data from meteorological registers.
This ends today's lecture. We talk about visual programming, generative design, and artificial intelligence in construction. Then we discussed lean construction and integrated project delivery, building life cycles, and asset management. Finally, we had structural health monitoring and digital twins. Thank you very much for your attention, and I invite you to the next lectures in the BIM Basic series.